Hey everyone, I welcome you all to today's session. Hope all are doing good today. So my name is Kiran. I'm glad to be on a success manager for today as well. Right. So before we go out, could you all please confirm if my voice is loud and clear? Thank you. Thank you, Nisha. So let me have a quick audio check with that right now. Hi Deepak.
Hi Kiran, how are you?
I'm good, Deepak. How are you?
Good, good.
Oh, thank you. Thank you so much. I'm
So I
handing over the
hope.
presenter.
Okay, sure. Hello. Please give me a confirmation if I'm audible, loud and clear. Yes. Okay. Great. Thanks for the confirmation. We'll just start in a couple of minutes, right? Okay. And the agenda for today's session is we're going to start with classification now, and we're going to learn various models of classification like logistic regression, support vector machine, where we are going to do decision trees, random forest, then we'll do naive Bayes, and we'll also do KNN means in the next 2 days, right? Okay, so and I hope all of you are practicing, very important. All of you are practicing so that you get accustomed, you get comfortable with the tool. Great. Thanks for the confirmation. Okay, so I'll just share my screen. Okay, so classification. I'll just wait for 1 more minute. I think people are still joining in. Okay, so classification. The word classification, what do you mean by the word classification? English, you can just layman, as a layman, what do you mean by the word classification? Divide into categories, divide into parts, right? Some categories, right? You have some. When it's classification, whenever you say classification, it means you are dividing or segregating or classifying, or should I say putting the data into categories, right? So let's understand classification. Okay, first let's understand what is classification, then we'll come to the example. It's a technique to determine the extent to which a data sample will or will not be part of a category or type, right? So classification models predict categorical class labels, very important, and it should be predict the categorical dependent variables, right? With labels, right? Okay, so let's take a look at this example which is there. A bank has to analyze if loans should be granted to all their customers, right? We have discussed this loan thing, right, earlier. Now, they have a bank. Whenever you go to a bank and ask for a loan, what do? They ask you to fill a format, right? They ask you to fill a form, and some details are there, a lot of details are there, right? Which you fill: name, address, location, your income level, your family members, and lot of other details, right? Any loan which you're already existing with the current bank, any loan that is existing with some other bank, your credit rating, and also many more questions, right? So age, employment status, and all these, right? So they are not taking these information just for the records, one, and second, these data that they are collecting, they have scientifically come to come to collect these data. I mean, they have scientifically decided that these are the variables which can help them predict. When they use this data, it can help them predict whether they should be granting a loan, whether they should be giving the loan to a new customer, or they should be giving a loan to you or not. Okay, so how do they do that classification? With the help of classification algorithms. Now, don't think only decision tree is the only classification model. They help them classify the data they collect historically. They help them on that historical data. Build, they train a model, right? And they build a model, and that model can be a class decision tree. It could be logistic. It could be random forest, right? Using any of these algorithms, the bank decides if a customer should be given a loan or not, right? Okay, so classification process includes two techniques. One, in first part, you construct the model, right? In the first part, you are constructing the model, and second part is about the usage of the model that is constructed. So model construction is done to describe a set of predetermined classes. So understand here, when I am saying predetermined classes, can you tell me this is supervised or unsupervised? You can just type S or N. S, supervised, because I have the data for the classes. I have Y variable which is split into classes, which already has some classes based on the historical data, right? Every sample belongs to a predefined class, right? Loan given, not given, loan given, given, not given, right? So that is how, because historical data will be complete, it will have my Y variable as well as the independent variables. Y variable, when I say, I mean dependent variable, right? The model is represented as decision tree, classification rules, or mathematical formula. Now, here again, as I said, the model can be represented by either decision tree, logistic, random forest, right? We're going to see naive Bayes also today, not, if not today, tomorrow, naive Bayes, KNN. So various models can be used to predict the classes of the data. Model usage. It is done to done to classify unknown. Now, when the model is trained, right? We all know we test the model, right? So on unknown data. So first, before we deploy the model, we test it on trained data, and when and after you test it, you deploy it in the real time environment on the unknown data, right? Done to classify unknown and future objects and to estimate the accuracy of the model. Now, based on the training data, we also try and estimate the accuracy of the model. We'll see how we calculate the accuracy of the model in this case. So, the biggest takeaway here is that classification models, in the classification models, my dependent variable is a categorical variable, right? If your dependent variable is price, you will, which model you will use? Which model can be used? Price, which is a continuous variable. Let me see how many of you have revised what we have done. If your model is having a continuous dependent variable, if your data is having a continuous dependent variable, which model will be used? Not unsupervised. Unsupervised is anyways not a model, it's a category, right? Again, supervised and unsupervised are categories of data. No one? Exactly. Regression. Remember in regression, what was our dependent variable? It was continuous. Okay? So, no one else is able to recall that, or still you are able to recall? Okay, when we'll do logistic, you will further uh, recall this and we'll further revise it once more. Okay. So accuracy is the percentage of test samples. Now, how is the accuracy calculated? The accuracy rate is the percentage of test samples, test set samples correctly classified by the models. Now, how do you calculate the accuracy? Let me just open classification, logistic. Okay. So I think I created one classification sample association. So, okay, I'll create an example here only. Example for classification. Let's say I go to bank for a loan. I'll take a bank loan, or let's take another example of a telecom subscriber. Telecom subscriber company wants to predict whether the subscriber is going to stay or not stay. Okay, that is why Y variable, whether they are going to stay with me or not stay. So they collect some data, right? Some variables they collect like your uh, duration with the subscriber, right? Um, your l- customer care calls in the last 6 months, some more like your latest bill. Yes, you can plan maybe, and plans also are classified, right? Plan 1, plan 2, then latest bill amount, plan, then maybe some more, right? Uh, delay in payment. No, network web. they all currently belong to the same network, right? That is why we want to now identify whether they are going to stay or not stay. Okay, connectivity. Okay, whether you are having connectivity issues or not, right? Let me take that also, right? Connectivity issues, right? So, some, I mean, I'm just randomly hooking up these, right? So based on these, the historical data, when they collected historical data, so this is my historical data. Okay, so it was uh, stay. I'll just type stay and NS, S and NS. Historically stay, NS, NS, stay, NS, NS, stay, stay, 6, 9, and stay. Okay, so based on these, this was my Y historically. Okay, now when you and let's say when I predict, when I put these variables in the model, right, I come up with some classification by the model, right? Let's call it as Y hat. Okay, now Y hat says, Y hat is able to classify them as stay, not stay, stay, mm, stay, stay, not stay, not stay, stay, and stay, right? So how is the accuracy of the model calculated? Wherever the model is able to predict correctly, correct prediction, right? I'll just put 1 for correct prediction and 0 for not correct. Correct, not correct, 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 and correct, right? So accuracy of the model is going to be wherever I have made a correct prediction, whether that prediction is for stay or not stay. Like, so here these are true positives, stay as stay, right? And these are false negatives, stay as not stay. I'm saying they will not stay, but actually they stayed, right? Right? So these are true positives. I have been able to correctly predict stay, right? So stay as stay are true positives, right? Stay as not stay are false negatives. I have wrongly, falsely predicted them as negative, but they were correct, right? And these are exactly type 4. You don't have type 4, but yeah, you can say that, right? There are only two types of errors, right? False negative is type 2 error, right? And this one, can you tell me, this is type 1 error, right? Not stay, false. So these are false positives, right? Exactly, right? This is true positive. Are you getting this? How this, how 80% accuracy came? I I'll just check how many were correctly predicted, right? Out of total, right? So these are true negatives, 2 negative and 2 positives. Getting this? So that's how you measure the correct accuracy, and you measure this accuracy with the help of a tool, and we'll discuss that. That is called uh, classification. No, not classification. Matrix. What do you call the name? I just always slip it. It's called confusion matrix. Sorry. Yeah. This is called, we measure, we create a confusion matrix wherein, and this confusion matrix simulates our very closely, it simulates our uh, hypothesis error, right? 1 as 1. How many did I predict 1 as 1? 1, 2, 3, 4, right? And 5. 5 I predicted. So these are my actuals and these are my predictions, right? So actual as 1 and means I can put S and NS and S and NS, right? Actual stay, and I also, my model also predicted stay 5, right? Actually it was not as NS, and my model also predicted NS 2. So I think we had 6, then 1, 2, 3, yes, 6. 6 S as S. Getting it? All of you are getting it? So 8 is the accuracy. Similarly, S as NS, I have S and NS 1, and this also 1. So on the diagonal, I have the correct, and these, this helps me calculate the accuracy. Is this clear? Confusion matrix that we create. So for all classification models, confusion matrix is what we create to measure the accuracy. Is that clear? All of you? Any doubt regarding this? Let me know, else we'll quickly proceed to the models now. Any doubt? No? Bharat, you got this? Yes? Then confusion matrix, remember in sorry, that hypothesis also, predictions. We had actuals and we predictions. We have predicted and actual, right? Here I have plotted stay and not stay, and my actual stay customers whom actually stayed with my network, and my model also predicted that they will stay. How many of them are there? Stay 1, stay 2, 2, 3, and these 3, 6. So you just have to plot them, stay and not stay, right? Stay as not stay. My model predicted this wrong. Stay as not stay. Got it? Confusion matrix, right? We'll be doing confusion matrix in detail. This is just a very small example I've taken. Okay, so that's how you measure the accuracy of the model. Okay, now this is a quick example. How do you construct the model based on the features, based on the input variables, right? We create a classifier model and then we create some rules, right? And then based on those rules, we start predicting the unseen data. Okay, let me quickly take this example also. Model construction. For example, this is the data given, and you want to predict whether a person is tenured or not. Notice my tenured here is a categorical variable. Yes or no. Whether the teacher that comes in or the professor that comes in, is he a tenured professor or not? Mike came in, he was assistant professor. He had 6 years of experience, and our university classified him as not tenured. Bill came in, 7 years of experience, and he was classified as historical. This is historical data, right? Tenured. He was an assistant professor. Similarly, Dave, assistant professor, 3 years of experience, was classified as not tenured. And Anne, she was a professor and with 2 years of experience, and she was classified as tenured. Right? When I put this data in the model, it's going to create some rules based on the data. And what is the rule the model created? If rank is equal to professor, or see, if the rank is professor, it will classify it as tenured. Now, this is a very small example, right? There can be many more dependent variables or independent variables, right? Okay, or years is greater than 6. See, till 6 years, it classified assistant professors also as not tenured. From seventh year, it started classifying as tenured, right? So I created this rule. Very simple, simplistic case, right? My classification algorithm created this rule. And then when new data comes in, unseen data, so this is your, you can say, test data, wherein you will not give this variable to the model, and you will give only this variable, and it starts classifying into categories. So Joseph, okay, so this is the test data. I think, yeah, this is test data, wherein when I deploy that model, when I use test data, this is training data. Now this is the test data. When I use this data, it classified Joseph, assistant professor, and 7 years. It classified as yes, right? Assistant professor 2 years, no. Assistant professor 7 years. Merlisa, notice it classified Merlisa wrongly, right? Just the way I showed it to you on Excel. There can be model will not be 100% accurate, right? We can't. Our model is not God, right? So it made an error. It classified Merlisa as a not tenured person, though it should she should be a tenured, right? Then George, professor, 5 years, it correctly classifies. So if I look at the accuracy here, it's 75%. Only one is wrong. The three are correct, right? Now, when I deploy this model, unseen data, Jeff, professor, 4 years, what should it classify as? Professor, 4 years. It will classify it as tenured, right? Because Jeff is a professor. Is that clear? Right? How things work when we work with classification models? Please give me a confirmation. Right? Okay, now we are going to do some classification algorithms. We're going to start with logistic and support vector machine today, and then we'll do these tomorrow. If we have time, we'll start with naive Bayes today, right? Okay, so let's start with logistic, right? And for logistic, I will take you to another document which I have created so that we can have a good understanding of the logistic regression. Okay, regression, all of you know, so I'm just skipping this. Logistic. Now, types of regression. The most commonly, there are three types of regressions. Like linear, we have already done, right? Establish a linear relationship between dependent continuous variable. Remember this? And in a linear regression, which we did on Friday, our dependent variable is a continuous variable and independent variables. Independent can be any, right? Then you will have polynomial regression, means higher degree regressions, non-linear regressions, right? It established non-linear relationship between dependent and independent variable. We don't have this in our curriculum, but yeah, I've given you, this is another type of regression. Then third, logistic regression is what we are going to do now. It's a technique when dependent variable is categorical. Now, this is the most important distinction between logistic and linear. Remember this. Dependent variable is categorical. You can only have categories of data there, and your data will be in the form of true, false, yes, no, right? Is that clear? 1, 0. Okay. So logistic regression seeks to model. Now, how can how can you put some put the data? How can you classify the data into categories, right? It models the probability of an event occurring depending on the values of independent variable, which can be both categorical or numeric. Means logistic regression tries to model the probability of the event occurring. So it will try here to model the probability. Now, what is the probability that based on these X variables, my subscriber is going to stay? If that probability is greater than the threshold means the cutoff, right? I will have a cutoff, and let's take by default, let's take the cutoff as 0.5, right? So if the probability of based on this, I am going to calculate the probability of the event, and if that probability is greater than 0.5, right? It will classify it as stay, right? As 1, right? If that probability is of occurrence, probability of the subscriber leaving the network is less than 0.5, I will, sorry, probability of the subscriber staying with us is less than 0.5, right? Less than, and this is more than. If it is more than 0.5, that is our uh, normal rule also, right? In mathematics, when we do rounding, right? So whatever is greater than 0.5, we treat it as 1, right? So that we apply that same rule. Whatever is less than 0.5, I treat it as 0. That it will not stay, and this is stay, and this is not stay. Clear? Is that clear to all of you? How does how does it model the probability? That is what we will see. Though that is that is it's a lot of dirty calculation happens at the back end, right? We don't have to learn how to. So we can create a rule, Angela. If it is 0.5, I'm going to take it as, let's say I'm going to take it as yes. So I can create that rule. If it is 0.5 also, I'll take it as yes. Okay. Okay. Now it models the probability. Now logistic regression tries to estimate the probability that an event occurs for a randomly selected observation versus the probability that the event does not occur. Right? That is what I just explained. It predicts the effect of the series of variables on binary categorical response variable, right? On a binary categorical response. Notice binary, word binary. Means it is usually we perform logistic regression whenever my uh, cat, dependent variable is binary. Win, lose, 0, 1, pass, fail, healthy, sick, right? Leave the network, not leave the network. Getting it? So it's a binary classification. Okay. Usually we do it this way, but yes, we can apply higher level logistic, more advanced logistic models, which can apply on even 3 categories also, but that we don't have right now in our curriculum. Okay. So response, it classifies the observations by estimating the probability that an observation is in a particular category of a dependent variable, right? And used to classify binary classification problems. I should mention it that um, in most of the cases, right, we use binary classification problems. Is it clear, logistic? Right. So this is just a comparison of linear, simple linear, multiple linear. I have given some examples. You can go through it, though I've discussed most of them. Right. So yeah, logistic. Dependent variable is my categorical variable. Always remember this. Dependent variable cannot be price or sales or profit. It will be a categorical variable. Yes, no, 1, 0, true, false, healthy, unhealthy, right? Independent variable can be two or more, continuous or categorical. Relationship between them need not be linear. And some examples: email, spam or not spam, loan given or loan not given, student will pass or not pass. So in real life scenarios, you will observe, especially in business, we are dealing with a lot of categorical dependent variables. We want to predict bank, customer will give, we should give loan or not, customer takes offer or not take offer, right? So all these are examples of categorical variables, dependent categorical variables. Let me quickly discuss some examples here, and then we'll move to the logistic regression. Okay, credit scoring. Logistic regression is widely used in credit scoring, right? Is widely used and acceptable technique of credit scoring. Bank collects the data from person whom who comes to get a loan. I've already discussed this, right? Their analytics team try to analyze the data collected, and then the data scientists try to predict if the bank should give loan to new person who applies for the loan. Medical. Based on the medical records, historical records for the people in the city, we try to predict whether a person is going to have diabetes in future or not. Again, categorical data, logistic can be applied. Two categories, right? Hotel booking, a very interesting. Looking at the profile of the customer, their browsing history, personal spending, details, we try to predict if the person is going to book the hotel or not from the website. Telecom subscriber, again, I've discussed this example, so I'll just not read it, right? We know, right? Okay, so various real life scenarios you can try and predict using the logistic regression, right? Okay, now now let's take a look at the back, I mean the logic, how we come to the probabilities, right? Linear model is not a good fit for a categorical variable. Do you all agree? Yes? The linear model, if this is my linear model, and I have only two categories, 0 and 1. Can a linear model predict my categorical data? Not possible. That is what is shown here, right? That is what this first chart is showing. Now, how do you transform it into a logistic regression, right? As we cater, as we create a scatter plot, the dependent categorical variable y can take up either 0 and 1 value, right? The linear model does not fit appropriately in such dichotomous data. Made to fit. Now, how do you make, how do you fit this model? You just clip them, right? You try to clip them so that at least it is covering most of the, it is predicting, there are some lines which are predicting 1 and 0, right? So logistic regression model is created by is made to fit by clipping the ends to cover the data points, right? So we clip them on both the ends, but such a line cannot formulate a single formula, right? I cannot have a single line. I have three lines, right? One, then 2 and 3, right? So I cannot have a single line anyways. If I smoothen the edges of these lines, right, I come up with this S-shaped curve, right? And this is called a sigmoid function. So this sigmoid function can help you model such a scatter plot, okay? And how does it do this? We'll see. Along with sigmoid function, see, sigmoid function has probability on the y axis, right? And we know 0 and 1. and we have probability 0.5 in between. So any data that has a probability greater than 0.5, I will classify as 1, and less than 0.5, I'll classify as 0, right? So this is called my decision boundary. This is cutoff is called my decision boundary. Okay. The main reason why we use sigmoid is because it exists between 0 and 1. Now this sigmoid is a mathematical function. You don't have to remember these, just remembering that yes, we use a sigmoid function. You don't have to learn how to construct a sigmoid function. Okay. I'm just, in fact, in most of our, most of the batches I take, I don't even discuss this in detail. But yes, I thought that you should at least know. I mean, off late, I thought that we should know at least what is the background, what is the backend transformation happening, right? So I am, so I've started discussing this because it makes a lot of the learners, they are able to relate with this discussion. Okay. So the main reason why we use sigmoid function is because it exists between 0 and 1. Therefore, it is specially used on machine learning models where we have to predict the probability of an output. Okay, we use sigmoid function in machine learning where we have to predict the probability. Since probability of anything can be between 0 and 1, sigmoid is the right choice. So I've already discussed this, right? If p is greater than 1, output is marked as true. P is less than 1, output is marked as false. Okay. Right now, how do you arrive at this sigmoid function? See, we start with the odds ratio. Now, what is odds ratio? Probability of an event occurring divided by probability of an event not occurring. Okay, it's called a odd ratio. For example, when we flip a fair coin, the odds ratio is 1, right? When we roll a fair die for 1 and 2, only 1 and 2, odds ratio is 2 by 6, right? Which is, sorry, 2 by 4. It should be 4. Wait, 1 by failure. Yeah, correct. 0.3 upon 0.6 means 2 upon 4. Probability of failure is 3, 4, 5, 6, right? I want the, if I roll a dice, what is the probability of success? If I want only 1 and 2, probability of success is 2. What is the probability of failure? At the bottom we have 4, 2 by 4. So I get 1 by 2, right? In a deck of card diamonds, I've just given some example here, right? You can, so, right, that way you calculate the odds ratio. Then when you calculate the odds ratio of an independent variable in logistic regression depends how the odds change with 1 unit increase in the independent variable holding all others variable constant. The odds ratio represents the constant effect of the predictor variable x on the likelihood that the outcome will occur, right? That one outcome will occur. Okay. So if the odds ratio is greater than 1, right? If the odds ratio is greater than 1, it means it has 2 points, like in this case, the odds of getting a head on the loaded coin. Loaded coin means which is not a fair coin. Okay. Loaded coin means maybe it has some some manipulation is done, right? So odds of, let's say, but otherwise we know the odds of getting a head or a tail is 1 only, right? It's 0.5 only, or odds is 1 rather. Probability is 0.5, but odds are 1. Okay. So loaded coin is 2.33 times greater than that of a fair coin, right? If we want to, if I compare it with a fair coin and a loaded coin, the odds ratio is 2.33. These are just examples. Okay. Now coming to how do we come based on odds ratio, how do we come and create or transform it into a sigmoid function? Okay. The goal of logistic regression is to estimate the unknown probability for a given linear combination of independent variables. Thus, to arrive at these probabilities, we need to link our linear combination of independent variables to essentially the Bernoulli's distribution and map the linear. Bernoulli's distribution is nothing but the simple probability of success or probability of failure, right? Means if I have probability of, I know the probability of success or probability of an event occurring is 0.6, then probability of failure is 1 minus p, which is 0.4. Bernoulli's distribution assumes that it is the most simplified case of a random variable, right? Simplest form of a random variable means only two outcomes are possible, right? Either success or failure. Okay, so if I know the probability of success, my probability of failure will be 1 minus probability of success. Okay, and based on, and then the odds ratio will be P upon Q. Okay, that is Bernoulli's distribution. What I have just discussed in odds ratio is nothing but Bernoulli's distribution. Okay, so how do you convert this into, when you have the odds ratio, how do you convert it into a logistic or a sigmoid function? You do a log of this odds. When you do a log of odds, we call it logit function, right? And this is the natural log of odds is called a logit function, which helps us do this. And this is how a logit function looks like, right? When you plot the probabilities, this is how a logit function looks like. Between 0 and 1, you have on x, you have 0 between 0 and 1. Okay, all the probabilities between 0 and 1. Okay, for p, if you have p is equal to 0, then the logit of log, that is log of 0 is infinity. So you can see in 0 it's going to be infinite, and similarly p is equal to 1, then also logit is infinity, right? 1 in the denominator p, so it's 0 upon, it's 1 minus 1 0, so that is also infinity. So on both the sides you see the logit function is approaching infinity. For p is equal to 5, log of p equal to 5, my odd ratio is 1, log of 1 is 0, and you can see where p is 5.5, it is 0, right? Okay, so this helps me come to the logit function, and when I transpose this, transpose is what I have done, I have just transposed this, converting x into y, y into x. I come up with a sigmoid function. Okay, right? So this is just the mathematical transformation which we don't have to do. Do not worry. All you have to do is this: understand the decision boundary and that this sigmoid function models the probabilities. Okay, right? So that's the, this is again mathematically I've given, but you need not worry about it. Okay, right? So clear? How does a logistic function try to predict? Right? So I want all of you to open RStudio and logistic regression. I think I did not share this. Let me, can you give me, okay, this is a Google Drive, I got it. So classification, I'm sharing this classification. Yeah, I'm sharing it. Session 8, classification. So in that, go into logistic regression. It's there. So please pick up the data set LR underscore diabetes. Pick up this data set. I have also have a telecom example which I would, and I have also given the solution, I mean the model creation also. For that, you can go through that later, right? For now, just pick up logistic regression. And start importing this. Now, I will not tell you how to import this. I want you to do till line number 13. I want you to write, and I'm sure all of you know what is happening there. Import the data, run structure summary, understand the data, right? Structure summary. Once you're done till 13, type 13 in the chat window. Line number 13, once you're done, type 13 in the chat window. I'm waiting for your response. Let me also run it. Line number 13 done. No one? Have you imported? After importing, what is left? Just you have to view, run a structure. How many observations are there? Across how many variables? Exactly, 322 observations across 9 variables, right? So let's take a look at these variables. Let's take a look and understand these variables. Metadata, right? You have variables. SN number is just the line number. NPreg, number of pregnancy. Okay, what we have to do here? Okay, we are trying to predict if a patient is diabetic or not based on the given data, right? Based on the data given, we were trying to predict whether she is expected to be diabetic or not. Okay, NPreg, number of pregnancies in the past. Plasma glucose concentration, GLU. BP, diastolic blood pressure, some blood pressure. I even don't know, right? BP. So it has some levels, some blood pressure. Skin, triceps skin fold thickness. Some basically some classification has been done on these variables, right? Body mass index, diabetes pedigree function, age in years, and then last type. This is my, so of these, can you tell me which is my dependent variable? Type, right? It's classifying 1 and 0, right? Is that clear? Yes, type is my categorical variable, right? So when you run a structure, notice, keep an eye on the type. What is the classification, or what is the data type R has classified it into? What is the data type R has classified it into? Why? Data type I'm saying. What is the data type? Integer. Right? No, right now it's not Boolean. See, 0, 1, but R is taking them as numbers. Integer. Notice int. Right? R is taking them as integers. But should it be integer? My categorical variable, my dependent variable, should it be integer when I'm doing logistic? No. What it should be? Boolean, right? Yes. So Boolean are a type of factor variable categories. Yes. Right. So first thing I'm going to do is and you have to always keep an eye on the dependent variable, right? It has to be a factor variable. So I'll convert this into a factor variable as dot factor. I convert it and add another variable type 1, which is factor variable. Notice now, when I run this and I run a structure of type 1, I have added a type 1 variable, which is a factor variable. Yes? Clear? Next, CA tools. I'm sure we have installed this CA tool earlier, right? So call this package and we are going to split it into train and test. Again, line number 40 to 53. We have done it earlier, so I'll give you 2 minutes to write these. Set seed, you can just take it as same as mine so that we have a comparable output. Split ratio I have taken as 0.8. Why I have taken it as 0.8 higher? Because my observations are not, I mean, it's not a very big data I'm analyzing, right? Are you getting it? Why I have taken split ratio as 0.8? Had it been some data set in thousands of observations were there, I could have taken it at as 0.7, 0.75 also, right? Because in that case, most of my scenarios could have been covered with less amount of data. Okay. So split ratio as 0.8. And when you write and run the commands till 53, type 53 in the chat window. Nothing new we are doing here. Everything we have done earlier. Okay, great, Nisha. We'll wait for others also for confirmation. Let them. I'll just be back in a minute. As everyone is writing, I'll just get my bottle of water. No one has done till 53. 53 is done. Have you been able to? Sudha, you are getting an error. What is the error? Has to be 0 and 1. So what is your split ratio? Is equal to this error in split sample dot split. Yeah, I'm looking at it. So the error in sample split ratio parameter has to be I between 0 and 1. You have put it in 0 and 1 only. Why are you getting this mess? Split ratio parameter has to be strange. Anybody else is getting this error? Sample factor variable. Yeah, just check. Yeah. I think yes, right. Maybe she has not converted into factor. Got dive.1. Check this. Did you convert it into a factor variable? Sudha? But I think split ratio, it's saying into factor. Split ratio is 0.8. Sudha, just check. What is your, did you not done into factor? Okay, fine. Just do it. I think you missed that. And I think you are not having type 1 because you did not convert it into a factor variable. Now is it working? Bharat says regarding as dot factor, I can see two levels 0 and 1. Can you say what is the data? Why is data 2 and 1 sequence? Means, okay, this one. So it has converted into factor 1, factor 2. Okay, it has converted it into factor 1, factor 2. Okay, so this is one factor, this is second factor. It has converted into two, it has named the factor as 1 and 2. Okay, okay, it has named, see, 0 and 1 were integer. it has converted it into, okay, let me show this to you. Where did I convert this structure? Let's view this. After this, if I view div 1, levels, these are levels. 1 and 2 are levels. Okay, though this is same. So when in structure, it gives you levels, right? So 2 and 1 are levels. Level 1, level 2. Level 1 is 0, level 2 is 1. Okay? Okay. Bharat, is that okay? Gayatri, can you share your code as well? Okay, if I view now, Gayatri, is it done? Now, if I view my train data, you did not mention the, see, you are saying LR underscore diabetes. It should be diab 1, na? That you have converted, you would have converted it, or is it you have named it as LR diabetes? Okay. Did you name it as dive 1? So then you should put dive 1. Okay. Okay, fine. After this, view. Let's view our training data. Right? How many observations in the training data? How many observations in the training data? Who will tell me the number of observations in the training data? 265. Okay. Let's attach line number 64. I attach training data, and then creating a logistic model is using the command GLM. GLM stands for generalized linear model. Okay. And when I run this logistic model, line number 69, 70, and 71. Understand this? Just give me 1 minute and then you write the code. Just let me explain this. GLM stands for generalized linear model. Type 1 is is my dependent variable. Dot all the variables except type. Right? I don't want type, so I am just doing dot minus type, means remove the type from the model. Okay. Data, training data, and family equal to binomial. I have to add this family equal to binomial to run a logistic model. Clear? So run this with all the variables. The type of model I'm going to run. See, if you want to know the exact definition, I will write, let's take help from GLM, right? Understand generalized linear model. See, it will run the model, different types of model. Family is a description of distribution of the error distribution and the link function to be used in the model. GLM, this can be characterized family of functions basically, right? Binomial is one. Family function of the result is called a family function. GLM dot fit. You'll get the family. I think you should be getting the. See, binomial is one. Then you have some other details also on family, right? Gaussian is one. Okay. So, but for this, we have to remember family. If you want the more detail on family, you can take a look at this link, right? Where what are the different types of functions? Okay. Model. Have you? If I run the model, I get these coefficients. I get the intercept, these coefficients, and some degrees of freedom, some matrix called null deviance, residual deviance, and AIC, right? All of you are getting this same? Till line number 81, when you're done till line number 81, type 81 in the chat window. So we know, first of all, we know the importance of these significance codes, right? So triple star means you're 99.9% confident that the variable is significant. So basically it is telling you the significance level. The model is 99.99% confident, 99.9% confident. Then 2 star means it is 99% confident, 1 star means it is 95% confident, and dot, we don't have a dot here, it means it is 90% confident that the variable is significant. Okay. Now we have run, all of you would have got a similar output, right? When you run a summary, you would have got a similar output, right? So deviance residuals means deviation residuals, variation of the residuals, minimum deviation, maximum deviation, right? Okay, done till 81. So let's understand this output. To understand this output, I'm going to take you to the, so you have something called deviance here. First of all, you have seen null deviance and residual deviance, right? Now, what is a null deviance? Null deviance, if you remember in regression model, we had something called base model, right? Wherein you don't put any, you don't use any independent variable, right? What is the base and what was that value with that base model, right? Remember that base model? So what is the deviation in that base model when I'm not using any variable is called null deviance, right? First, let's understand what is a deviance. It's a measure of goodness of fit of a GLM, generalized linear model. How good my model is fitting. Higher the deviance value. Deviance is, I mean, you can take it as variance only, right? Higher the deviance value, poor is the model fit. More the variance, it means lesser the, I mean, the model is not of that good quality, right? Agreed? Null deviance. Null deviance indicates the deviation of the response variable predicted by the model with no independent variable. So you don't have any independent variable. When you don't put any independent variable, what is the deviance, right? That is called null deviance. But only the intercept. You just have the intercept there, right? So lower the value, better the model. Null deviance, lower the value, better the model. But now comes in residual. So you can't take decision just based on null deviance. Residual deviance. Now, when you put the variables in the model, just the way we have put, right, the independent variables, what do you think should happen to the null deviance? It should increase or it should decrease? Logically, tell me. There is some minimum amount of variance that is there. Now, when I start putting in more variables, do you think that variation should decrease or increase? I'm starting put, why increase? Starting putting Sachin, I'm starting to add more information. When I start to add more information, I am putting in more data. So will it decrease or increase? See, when you start to add more information, your model will become more sharp. It will become more robust, right? With more data. Sachin, are you getting it? Right? So residual deviance. Now, when you null deviance indicates deviation of the response from the actual predicted by the model on adding independent variables. Now this is the rather it should be residual deviance. My bad, right? This should be residual. Residual deviance. I'll correct it and again share it. Right, right. So residual deviance indicates the deviation of the response from the actual predicted by the model on adding independent variables. So lower this deviance. Now lower the value of this residual deviance. Better the model, right? Let's say I have to, so the more, if I start putting in more variables, my, what will be my target, or what will be my goal? I should be able to minimize the variance. Yes, are you agreeing? Right, I should be able to minimize the variance. Means residual variance I should be able to minimize when I'm trying different alterations, or when I'm trying different iterations of the model. My, I am going to pick the model with the least amount of residual deviance. Okay, and another interesting thing, more the difference between null and residual. See, I had some null which is constant, right? When no independent variable was there, right? I started adding variables. I added 2 variables, 3 variables, 4 variables, and my, I started getting residual deviance. As I added more and more variables, my residual deviance started getting low and low, right? So which is the one I'm going to pick? Model which I'm going to pick? The model having the least residual deviance. It means the difference between these two is the maximum, right? More the difference between null and residual, better the model performance. Because that is the value added. This is the value added, right? You are able to reduce the variance, means you are adding value. Your model is really adding value to the null deviance. Clear? Is this point clear to all of you? Null and residual, right? Okay. Then you have another AIC, and before that you have degrees of freedom. Degrees of freedom is total number of observations in my model that I have put in the model minus the variables, right? So total number of observations for null deviance was 264. If you remember, 265 minus 1, 264. And in residual deviance, my degrees of freedom is 265 minus the observations that I've, oh sorry, minus the variables that I've used in the model. Okay, that will give me my degrees of freedom for the residual deviance. Okay, so yeah, degrees of freedom for null, as I mentioned, it's n minus 1. For residual, it's going to be n minus k minus 1. Okay, and degrees of freedom associated with null and residual differs only with k. You can easily see, right? Okay, next AIC. There is, can you explain degrees of freedom? Okay. See, what is meant by degrees of freedom, Bharat? Remember, I have explained degrees of freedom. The independent values that you can put in a model, right? Or put the independent values that you can put. Remember that? So degrees of freedom here is, for null, it's pretty normal n minus 1, because I am not using any variables, right? For residual, you just remember it as n minus k, where k is the number of variables used in the model. See how many variables I'm using in the model? 1, 2, 3, 4, 5, 6, 7, 7 variables, right? Or is it SN number is also used right now. So 8 variables, right? So my degrees of freedom will be 264 minus 8. 265 minus 1 minus 8. 256. Okay, right? Okay, now coming to AIC, Archaic Information Criteria. This is another metric you can see in the model, output of the model, right? What is this AIC? AIC in logistic regression is analogous to adjusted R square. Remember adjusted R square in linear? What is adjusted R square? Who will tell me? Remember, anyone remembers? It's the R square with only the significant variables. R square was coefficient of determination wherein we are calculating the percentage of the model percentage that my model is able to predict, right? The explained variation, if you remember, right? The percentage of the variation my model is able to explain. R square calculated that coefficient of determination, remember? And adjusted R square is the coefficient of the variation my model is able to predict only with the significant variables, only the variables which are with star, which I'm going to take, only significant variables. Okay, adjusted R square. Now AIC is analogous, it's similar as adjusted R square in linear regression, where it tries to prevent you from including irrelevant predictor variables. Remember, if you add more variables, we have to, if adding more variables does not add value to our model, it means it is not able to reduce my variation. Does it make sense to add more variable? No, if that variable is not adding any value, it does not make sense, right? So it is a measure of goodness of fit which penalizes the model for the number of model coefficient. Means more the number of coefficient you are using, more the variables you are using, it penalizes you on that. Okay, useful when we have to compare the goodness of fit of more models. It is used to compare with 2 or more models, right? It is a maximum likelihood estimate, means how well the model predicts the data, which penalizes to prevent overfitting. If you remember overfitting, when does overfitting happen? When I am just chasing R square and I just keep on putting more variables and try to increase my R square, right? Try to increase my explained variation. So AIC penalizes you if you are adding more variable, right? And it is not adding any value. So it tries to prevent you from overfitting, and it tries to prevent you to add unnecessary variables which do not add value. Okay, it is a measure of flexibility of the model. Lower the AIC, better the model. The rule here is lower the AIC, better the model. If I'm comparing 2 models, lower AIC means better model. Okay, right? The best fit model according to AIC is the one that explains the greatest amount of variation using the fewest possible independent variables. Low for 2 models, Vaibhav. Lower when I compare 2 models. Yeah, I'm comparing when it is used. See, it will be used when you have to when you're comparing, when we have to compare the goodness of fit of 2 models. Okay, clear? So rule here is lower the AIC, better the model. The best fit model according to AIC is the one that explains the greatest amount of variation using the fewest possible independent variables, right? So it does not allow you to unnecessarily put more. It penalizes you. It means it will AIC will increase if I am putting additional variable in my model which is not adding much value. It will increase my AIC, right? Is that clear? AIC is clear to all of you? Now, Fisher scoring iteration, this is just information that how many iterations did the model go through at the back end. So there were 5 iterations of this model run at the back end before arriving at this output. Not much of significance when we are trying to evaluate the model. Okay, but yeah, Fisher scoring algorithm is the derivative of Newton's method for solving maximum likelihood problems numerically. It tells you the model, how the model was estimated, how many iterations did it take. The algorithm looks around to see if the fit would be improved by using different estimates. If it improves, then the model moves in that direction. So it tries to do some iterations at the back end, right? And how many iterations it has done, this is given by this Fisher um scoring iteration, though we don't use this in uh, arriving at the final model. Okay, it tells you how many iterations did the algorithm run before it stopped. Okay, clear? Right now, what we'll do is I've explained this, so this is all written here also. So I'm just skipping this everything. Let's try and run some iterations. What I'm do is I have included right now. I have included all the variables in my model. Let's remove age from the model. So I am removing right now age. So I am running line number 117, 18, and 19. Run line number 117, 18, and 19. And of course 121 also. Name it as model 1 so that you are able to differentiate it from the model 0 or the normal model or the main model with all the variants, with all the variables. When you're done till 21, type 1 to 1. We'll wait for others. Can I get some more confirmations once you're done till 1 to 1? Okay, good. So when I removed age, what happened to my residual deviance? Can you see it got increased a little bit? Variance increased? Yes? Just observe a little bit, right? Yes? So it means if I'm removing age, my variation is increasing. Means age is a significant variable, right? Let's take a look at AIC also. AIC, what happened to AIC? 238.64 and it became 236. Notice. So AIC has reduced, right? No, sorry. Yeah, AIC has reduced, but variation has increased, right? So here both of them are moving in opposite direction, right? But if I look at variation, it means I my variation I am not able to explain it to the best possible if I just remove age, right? So age, it means age is a significant variable and I am not going to exclude it, right? Because it has increased my variation. Okay, so let's run another iteration. This time I'm going to include, see here the AIC and this deviation. What variation are you looking at? Residual deviation, residual deviance, Angela. Okay, see null is going to remain the same only, right? Because null will remain same. It is a variation when you do not put any variable. Okay. Okay. So let's now remove let's include age, and this time let's remove BP. Again the same thing, line number 131 and 132 and 133, and then I run a summary. Yeah, you can say, okay, good, thanks. I've just indented it, right? Now, again, you see variation is increasing when I removed BP. And what happened to AIC? AIC has decreased again, right? So looking at the variation, I can say that I will not be removing BP also, right? Let's remove NPreg, number of pregnancies. Model 3, you can name it as model 3. See here, there is a very slight variation. There is a very slight decrease in AIC, right? So here we have to take a call. We can run, if I run model 3, where I remove pregnancies, AIC has increased significantly, notice. Increased significantly, quite significantly compared to the previous ones. Yes, Weber? Yes? So it indicates that even NPreg is an important variable, and also the deviance, if you see, the deviance also increased quite significantly. Summary model from 220 to 231, 11, increase of 11, and AIC. So it means NPreg is also a very important variable. I cannot remove that. Let's check for skin. So this is how you do iterations. You keep on removing some variables, right, and checking how the variables are behaving, right? Model 4. Let's see model 4. What happens? If I remove skin, my residual deviance increased a bit, very little bit, right? But AIC has also increased, right? AIC is also increased compared, no, wait. AIC has also increased, right? Model 4. Oh, did I run model 4? No, I did not. Wait. So model 4, AIC has decreased, right? And my residual deviance has increased a very little bit. AIC has decreased and residual variance has increased a very little bit, right? So see, now when you run these iterations and you observe these residual variance and AIC, see, you can take a decision here whether to include skin or not. You may want to exclude skin because a very slight increase in there in residual deviance, but AIC, there is a significant 2-point decrease, right? So for skin you can take a decision whether you want to include or not, right? So if I exclude skin, right, then I will take model 4. If I include skin, I will take the original model, right? Now what I have done is I am trying to after we have run the fourth model, we'll try to calculate the accuracy for both model 4 and the original model, right? And we calculate the accuracy of the model. First we'll try to predict. Yeah, first we have to predict in the test. In the test data, I will try to predict the type, right? So I am predicting this in line number 172 and 173 for model 4. So let me write it as model 4 prediction and model prediction, right? Original model prediction. Okay. Quickly do this. Predict. The command here is predict for prediction. So you get some probabilities, right? When you predict, you get some probabilities. I'll just take 3-4 minutes, and when we come to confusion matrix, we will take a pause. We'll go for a break. Let me explain. When you're done till 178, type 178. Okay. So are you seeing, sir, it's sometimes it becomes so tricky, you're not able to take decision. So now it will depend, lot of other factors will come in, like business experts. You can take help from business experts, whether you should be including skin or not, right? Because it is significantly reducing my AIC, but a very minor increase in the residual was there, right? Okay, herein the industry expertise come in, whether diabetes and skin are really, there is some correlation between them or not. Okay, done. 178. Others. Now if you see, let's talk about model 4. It is predicting 3, the third observation, as it is giving a probability of 3%. So should this be a case of 1 or 0? Diabetes or no diabetes? No diabetes, because it will round it off to 0. Yes, right? So patient 3 has been diabetic. Check this. Yeah, let's check this in test data. What is patient 3? My patient 3 was 0 only. So my model has correctly predicted it. Are you getting this? My patient 3 was 0, and my model is also predicting it to be 0, right? Fourth model, right? Let's take a look at 4, 5%, 0, but here there is an error it is making, right? Similarly, if I talk about 14, 60%, and here my model predicts, again it's wrong, right? 27, 85, again it is wrong. Then 28, 13%, it predicts correctly, right? So can you see now? Now I cannot go through all the 265 like this. So I will create a confusion matrix, right? I will create a confusion matrix. So do you want to do confusion matrix right now? Let's do it. It will hardly take 2 minutes, right? Let's create a table, right? We'll just complete it. Otherwise the momentum will be lost, right? So let's create a table, and what I'm saying is actual value. This is a variable. Actual value is this type 1, and predicted value is equal to the the RES value which I've got where it is greater than 0.5. So I create this, and when I get the confusion matrix from table 4, let's talk about 4, model 4. Res 4. First write 197 and 198. See, my original model, I have calculated the confusion matrix for both of these. You write it, then I'll explain. There is hardly any difference in the prediction. Just a very minor improvement. But of course, since there is an improvement, I am going to go with model 4. Can you see? When I see the confusion matrix of model 4, I have the accuracy level. But yes, even if there is a little bit of improvement, I have an accuracy level of 77%. But if I see the accuracy level of the other one, it is 38 plus 13 divided by 38 plus 13 plus 9 plus 7, right? So what is the accuracy? 76. With the model wherein I have included all the variables, my accuracy is 76. Otherwise, it is, if I remove skin, it increases. Accuracy increases. It means I should be removing skin. Yes, got it? Confusion matrix, right? Okay. Now we'll learn the confusion matrix in post the break, right? So we'll take a break. Hopefully, uh, you are learning, you, and this session has added value, and you have learned a lot, and you have enjoyed it also. That is more important. Enjoying is also very important. So I am opening up the poll. Please do participate in the poll. Let us know how did you do in terms of pace and delivery. The poll is open now, and I'll see you in 20 minutes, right? Exactly 20 minutes. We'll come back and we'll continue with confusion metrics. Okay. Please to come back as per the timer. Hello everyone. Thank you so much for participating in the poll. Please give me a confirmation if I'm audible loud and clear. Yes? Okay, great. Thank you. Okay. So we had created two confusion metrics, right? And we can easily see if I remove skin, I'm able to add to my accuracy, right? Now, let's understand confusion matrix in a little bit more detail. In fact, in great detail. Confusion matrix, right? Performance measurement tool for machine learning classifiers. Classifiers means classification algorithms, right? It is a tabular representation of actual versus predicted. Just a second. So it's a tabular representation of actual versus predicted. This helps us to find the accuracy of the model and avoid overfitting, right? It is a performance measurement tool for machine learning classifiers used to measure recall precision, sensitivity, specificity, and more importantly, AUC. We'll see what all these terms are, right? So now this is your confusion matrix, wherein these are actual values, these are predicted values. So when you predict 0 as 1, they are classified as false positives. Type 1 error, remember from the inferential statistics. So confusion matrix is very similar to actually the the errors you have done earlier, right? Type 1 error, then type 2 error, positives, actual value is positive, but you are predicting as negative. We have seen this in the example also, right? Then you have true negatives and true positives. We know this, so I'm not going to spend more time here. Now, true positives, okay, this is all done, all what I've explained. Okay, now what are these ratios? So total accuracy of the model, we have calculated this, right? True positive upon true negatives, these are the diagonal elements, right, upon total. Now what is specificity? There is a term called specificity which is equal to true negative rate. Means of the total negative, how many are my models predicted correctly, right? Of the total negative, that is called specificity. True negative upon true negative plus false positive. False positives are negatives which have been incorrectly classified as positives. So this gives you true negative. Oh, sorry, this gives you total negative at the bottom. Is that clear? So that is called specificity, true negative rate. Similarly, you have sensitivity, which is called true positive rate. True positive upon true positive plus false negative. Of all the positives, how many the model predicted correctly? Or both, of course, to get the maximum accuracy, both of them should be as high as possible. Is that clear? Specificity and sensitivity is clear to all of you? Type S if it is clear. S in the chat window. S for specificity and sensitivity both. Right? Just type S if it is clear. Okay. False positive rate. So what is false positive rate? 1 minus specificity, right? False positive upon. So it is, if I want to calculate the false positive rate, I'll deduct it from 1, specificity from 1, and this is the formula. Similarly, false negative rate, 1 minus sensitivity. Is that clear? Right? Now, coming to another important tool for understanding the accuracy of the model. ROC and AUC. ROC means receiver operating characteristic curve, ROC curve, and AUC is area under this curve. Right? Let's understand, try to understand this. ROC is the probability curve and AUC is area under the curve, represents the degree of measure of separability. Means what is the degree of the measure, what is the degree of measure of separability? It tells you how much model is capable of distinguishing between the classes. That is, how much my model is able to predict true as true and false as false. Okay, how better. Okay, so true positive rate. Remember what is true positive rate? The model sensitivity. True positive rate is the sensitivity. So total number of positive or the proportion of positive my model is predicting correctly. It should be as high as possible. Remember that, as high as possible. So it means the more my curve is, the more my curve is deeper here, right? The better will be my model, right? And deeper the curve, let me show it to you. Suppose this is my curve 1 and this is my, okay, I don't want it to be black, red, right? So this is my second curve, right? So it is having high TPR. So of this, if this is curve 1 and this is curve 2, which one will have more AUC, area under the curve? Which one will have more AUC? Should not take that long. Which one will have more AUC, area under the curve? 2, everyone agrees? So it means deeper this curve, better is going to be my model. Okay? So whenever I'm going to compare, right? I am going to pick up the model with a deeper ROC curve because it will be giving me more area under the curve, right? Okay, higher the AUC, better the model at predicting false as false and true as true. Okay, of course, higher the AUC, area under the curve, more is the model predicting TPR, true as true. And what is FPR? FPR has to be as low as possible. Then only I'll get this point, right? As low as possible. If FPR is high, then I will be reaching somewhere here, right? It will, of course, this will fade, right? It will fade. So at this point, this is the point which I would want to achieve, where I have the maximum TPR, right? ROC curve is plotted with TPR, that is sensitivity, plotted against FPR, which is 1 minus specificity, where TPR is on y-axis and FPR is on x-axis. AUC nears, now these are all probabilities, you know, right? Between 0 and 1. So what is the maximum AUC? If this is 0 and this is 1, maximum 1, and similarly this is 1. So what is the maximum area that can come under the curve? What is the maximum area that can come under the curve? This one? Yes. And what is this area? 1 unit by 1 unit. 1, right? So the more AUC is, it means better is the separability. So it means the model is a good measure of separability. AUC near to 1 means model has good separability, and AUC 0 means it has the worst separability. In fact, it is predicting 0 as 1 and 1 as 0. And when AUC is equal to 5, it means model has no class separation capacity whatsoever. Means if AUC is this line, it means model is not adding any value. It has no separation capacity. Okay, here ROC is clear to all of you? Now, ROC is a very common way to visualize the performance of binary classifier. Binary classifier has two outputs. This is all what I've explained, the same thing, right? If you want to read more about ROC, you can follow these links, lot of detail and different situations they have discussed, right? Okay. Now, this is already I've discussed. Okay, let's understand ROC from another perspective, right? How, let's assume we have a model which predicts whether the student will pass or fail. The model predicts probability of each student. Using these probabilities, we plot the distribution as shown. Now, these are the probabilities of the students passing, right? On the x-axis, I have the probabilities of the students passing. Okay, so red distribution, and so if my probability exceeds 50%, I have this green curve. But there are some, now this green curve is, red distribution represents students who failed and green represents the students who have passed their exam. Okay, this is actual how many of have passed their exams, and these are the expected probabilities. Okay, now we have to pick a threshold value above which now we have to pick a threshold value above which we will predict everyone as positive and below which we'll predict everyone as negative. We will set this threshold as 0.5. If I set the threshold as 0.5, now notice if I have set the threshold as 0.5, all these under this red curve, but on the left side of this green part, these are true negatives. My model, I am predicting, actually they failed. They are falling under this curve, and my model also predicted them as failed. These are the probabilities coming from the model, right? Expected probabilities, right? So these are true negatives. And what is this orange part? These actually, these people passed, but my model gave them a probability less than 0.5. Getting it? These are actually, they passed because they are on the green curve, but my model predicted them as failures. So these are false negatives. Getting it? False negative. Similarly, on the green side, the one under the green curve and to the right side of this red are true positives, and the one with this yellow shade are false positives. My model predicted them as pass because the probability given was greater than 0.5, but actually they failed. So false positive. Clear? Right? If you plot ROC this way, I mean you can plot it this way, and just an example to understand how does it classify all the fours: true negative, false negative, true positive, and false positive. Clear? Right? So let's quickly now go into R, and I've explained this, the same thing I've explained. I want you to download this package and activate it. So I'm sharing this code so that in the interest of time. So after the checking the accuracy of the confusion matrix, I select model 4, right? After checking the accuracy of the from the confusion matrix, we select model 4. I'll share this, right? I'll share this again. Okay, don't worry. Okay, so now this is the prediction. We have already done that. Let's call it res4. We have called it res4, I think. Yes, res4, same. So you need not write this. You can just take the earlier res4. We have already done res4 with the model, right? So need not write this. In fact, I'll just, all you have to do is press 4. Oh, I did not activate the library. So don't worry about the warning that is coming. So this is my confusion matrix. Oh, sorry, this is my ROC curve, and notice these points on the ROC curve. These indicates the cutoffs. So 0.5 right now, 0.5 is my cutoff. So I have a true positive rate closer to 60%. If you have done till 237, type 237 in the chat window. So prediction and performance, these are the syntax, these are the commands, okay? Performance means you try to plot the performance, you save it to ROCR PREF, and then you try to plot this performance, okay? Colorize equal to true means it is adding color. Every cutoff, when you decrease or increase the cutoff, right now we have a cutoff of this, right? So if I try to increase the cutoff, I will get a higher true positive rate, right? But with the impact on the false positive rate also. Okay, so that's how you plot the ROC curve and AUC. Okay, so that's about logistic regression. I also have another example. I want you to go through this telecom example. I've given you the entire codes about this, right? So you can go through it on the same lines, but it will be great if you revise what we have done, and then you can maybe try and work on telecom on your own, telecom example. Okay, so let's go to the next algorithm as a classifier, which is, let's take it as SVM. Let's do SVM right now. Okay, SVM, we'll do SVM. Logistic, we have done support vector machine. SVM means support vector machine. Now, what is SVM? What is support vector machine? Support vector machine are classification algorithms used to assign data to various classes. Means, can you see these black lines? They are trying to segregate my blue cross and red negatives, right? Now these are called the support vectors. Okay, are classification algorithms used to assign data to various classes. So there are two classes of data, right? These algorithms try to classify them in the best possible manner, right? They involve detecting hyperplanes. These are called hyperplanes, right? Sorry, these are called hyperplanes, my bad. Right? Support vectors are the nearest point to these hyperplanes on either side. Okay, so these they involve detecting hyperplanes, which are the decision boundaries, which segregate the data into classes, right? So notice, if I take this particular example, this is one support vector, right? Let me call this A, right? Notice the points, this point and this point, these 2 points are very closer to that of A, isn't it? Yes. So this is one hyperplane. Then I have another hyperplane. Let's name it as B. This one. Okay. Let's name this as B. Hyperplane B. Blue color, but don't get confuse it with the blue and red uh, data points. Okay. This is my B hyperplane. It has some significant, some good amount of distance with the closest data points, isn't it? There is a difference of this and there is a difference of this. Sorry, this much at least. This much, right? This difference is there, right? With the blue. Just ignore this other one, right? So, which of these do you think is a better hyperplane? A or B? Did you get my question? Which of these do you think is better classifying my data? A or B? Anyone who says A? Anyone who says A? So I go with what Vaibhav I'm saying. Can you see my A? This is my A hyperplane. It is classifying data, right? But these, wait, I'll have to again plot it. Let me plot it with pink color. This is, sorry, this is my A hyperplane. I'll plot it in pink. Okay. It has points on either side very close to A. And then I have a B hyperplane which has points which are far away, little far than at least A. So which do you think is better classifying my data? A or B? Why A? Vaibhav, it has points very close to that of. So if there is a new data point that comes closer, it is not able to divide it properly. Saurav, can you just hold on for a minute? Do you want to speak to me? You can put it in the chat window if you have any doubt, or if you want to discuss, I can discuss it towards the end if you want to discuss anything. Okay, right? B not equidistance, Weber. What I'm saying is, it is, see, the data points, the distance. This distance is called the margin, right? The more the margin, it means my hyperplane is very easily classifying, right? Right? But this hyperplane is not very easily classifying. It has points very closer. If a new points come here, it might, if a new points come slightly, if suppose a minus class comes and it is just near to this data point, somewhere here, what will it classify? It will classify it as plus. Just a small difference. Yeah, it's like that, right? Got it? So that is what I'm saying. Exactly, yes. A is classifying, just managing to do that. So if there is a little bit variation in plus and minus, it's going to wrongly classify that, right? So hyperplane chosen should be such that all the points in the data set are as far as possible or far away from it. This helps in performing the classification easily. For example, in the given, see, that is what I was explaining. In this example, in the given graph, it is easy to classify point A and B. Now A and B are easily classified because they are far away, but C, it's difficult to classify C because a little bit variation in the, it will wrongly classify it as minus, right? But one cannot classify C confidently as the point is very close to the hyperplane, right? So that is what I was explaining. If I talk about this, the ideal hyperplane are Once the ideal hyperplane is discovered, new data points can be easily classified. The objective of optimization is to maximize the distance between the data points. These data points are called the support vectors, means the closest data points to the hyperplane, right? And the hyperplane, this distance is called the margin, means maximizing the the hyperplane that maximizes the distance between support vectors is the ideal hyperplane. Okay, and that is what we try to do when we do run support vectors. Okay, is that clear? This is just a mathematical derivation. I'm just going to skip this, right? And this is all what I've explained. Distance, maximize the distance, right? Okay, so let's now go to R, and we are going to run a support vector machine algorithm on Irish dataset, right? So for support vector machine, the package that is required is E1071. That is the name of the package, E1071. Whatever is visible till line number 18, you can do it. So I want you to write till line number 18. And when you are done, just type 18 in the chat window. Till line number 18. So what I'm doing here is, first I'm importing this data, or rather checking this data, viewing this data, and I've created a plot for this data, right? Then I am plotting sepal length and sepal width, right? So if I see sepal length and sepal width, I can create some lines, I can create some hyperplanes. One here and another one probably here, but if I create it's very difficult. You can see lot of errors will be there if I create another hyperplane like this, right? Lot of errors will be there, right? So what I'll do is I plot petal length and petal width. I just check another variable, petal length and petal width. Do you think we can create hyperplanes in this using petal length and petal width? Much better than sepal length and sepal width? One hyperplane I can easily create here, and another one I can create a hyperplane here with minimum amount of error. Isn't it? Isn't this? Yes, isn't it? So if I take sepal length and sepal width, I will not be able to classify in a very good way, or in a that will not give me better results. But if I try to create my SVM on petal length and petal width, I will be able to better classify, and that is what I have explained here. Analyzing the two scatter, sepal length and sepal width has a lot of overlap and not easy to distinguish. Petal length and petal width can better classify the data, so we will use petal length and petal width to run on SVM. Okay, so now I am going to create test and train data. Line number 26 to 43, in fact 45. Please write line number 26 till 45. Once you're done, type 45 in the chat window. Okay. We'll wait for others. Now, what is this doing? Line number 30, it is taking a sample of 100 random values from 150, right? I'll explain line number 30. And then if you see S, can you see these are 100 random values picked up from 1 to 150. Then I add these random values. I use these random values and pick up petal length and petal width from the iris dataset in line number 40, and I put them in train data. Another different way of classifying into train and test cross validation, right? So when I run line number 40, I just check iris train, iris dot train. You'll see these are the same random values, positions basically. Now these are the positions. Out of 150, I picked up randomly 100 and put them in train. Then similarly, I put the remaining in test. Okay, now SVM model. SVM model, I want to classify the species. See, understand this. On the train data, see this is my train data. let me view it. On the train data, this is my train data. I have to classify species, right? So this is my y variable based on the remaining two. So I put a dot, petal length and petal width. I put a dot. Data equal to iris dot train. Kernel means the model. I want to use a linear model only. I want the SVM algorithm should use a linear model. So we just mentioned kernel equal to linear. Cost. Cost means the margin. What is the margin that I want? Minimum margin I will accept. And scaling, while creating a model, do you want the scaling to happen? We always put scaling equal to yes. Okay. So SVM algorithm is used. SVM algorithm uses a set of mathematical functions which are called kernels. The function of kernel is to take data as input and transform it into a required form. Different SVM algorithms are use different type of kernel functions. Can these functions can be linear, non-linear, polynomial, right? Sigmoid. To read more about the kernel, I have given you the link. You can read more about the kernels. What are the different kernels that can be used in the SVM model? So sorry about this. So run line number 49, 50, 51, and 52, and I create a model. When I print this model, in line number 67, when you have written till line number 67, just let me know. After you print, just plot this model, SVM model on train data. When I plot this model on train data, these are the two hyperplane that are created. How many of you have done till 68? Type 68. Okay, we will wait for others to complete. Thanks for the confirmation. Others, I'm waiting. When you get a chance, can you share the PDF? Yeah, of course I will be sharing that. I've already shared it, Sachin. This one you're saying, right? This one. Yeah, it's already there. It's already there in the folder that I've shared today. Okay. Okay, I'll help you. I'll help you. Don't worry. It's not inside the SVM folder. It is outside. It is in the classification folder, right? It will be named as classification, something like that. I'll see. I'll see. Right? Don't worry. I'll just see if it is there. Okay, 68 is done. Now, tune. What does tune do? Tune help me find the optimal margin. Help me analyze the cost with different margins. Right? Tune help me analyze different costs, the cost and margins. Right? So let's say I want to check what should be my optimal cost or margin, right? So I write this command on line number 77 and 78, tune. I want tune on SVM, then species, data iris.train, kernel, and after this, till here it is okay, right? After this, I mention ranges is equal to list. I create a vector of cost wherein I mention different costs, okay? And I will check which should be my optimal cost. So run line number 77 and 78. I name it as tuned. And when you run a summary of tuned, I get some output. Run till 82. If you have run till 82, type 82 in the chat window. Others, can I get a response? Can I get a confirmation if you're done till 82? So that I can explain the output of this line number 82. Once you're done till 82, I'll explain the output of 82. Can you give me a confirmation on 82? Others? Still doing? Vaibhav, Lakshmi, Gayatri, Angela. Vaibhav done? Okay, good. Angela, Lakshmi, can you confirm so that because I have to explain this a little bit, it's a small explanation though. Now, okay, okay, still on it. You want me to wait? Okay, fine, I'll wait. Once you're done, just give me a confirmation for 82. Once you're done, you got an output like this. Okay, so when I run this, see what is this output that I'm getting, right? So I have 1, 2, 3, 4, 5, 6, 7. 7 at 7 different cost. I am trying to estimate the output. That estimate that which of them I should be selecting, right? Notice that when you have this dispersion starts just observe this dispersion. Wherever it becomes constant, start becoming constant, right? 1, 2, 3. Third, after third one, you can see it is becoming constant, right? Right? 51, 52, 51, it's becoming constant, right? So that is the most optimal cost I should include, that I should be including. And if you see, we have taken a cost of 0.04. So if I take a cost of 0.05, it will be slightly better. It may do a slightly better classification than 0.04. Okay, right? So that is what this tuning helps you to come up with, right? So we are going to go with 0.4 for now, and we'll create a confusion matrix, line number 86 and 87. I am just plotting the, from the test. I am just plotting the output of the test, and then I create a confusion matrix. And what I see is this model is giving me a error rate of 0.2 and an accuracy rate of 98%. It is now, this is a data set that is very much, you can say, a dummy data set, or it's meant to explain the learners, right? You, in a real scenario, you might not get that accuracy, right? That much accuracy, right? But yes, so Bharat, species, I think just check species. S is small, S is caps, right? Linear, kernel equal to linear, cost. You did not mention the range. SVM, you did not find SVM, it is saying. So you did not run this. You have to first activate the package. Line number 6, library E1071. Run this, activate it, okay? Bharat. No, for sure it is saying that you're not getting SVM. Tune. Okay, Vaibhav, in Tune, you are trying to estimate the best cost. You're trying to estimate the best cost or margin that we should take. So I've taken some margins. I've randomly taken some cost, right? And I'm testing which is the best cost I should take. You should take the best cost is the cost where the dispersion stabilizes. Like here, the third one. After the third one, you see this dispersion has stabilized 0.051, right? See, it is reduced. Can you see, from 0.25 to 0.15 to 0.05, and then it stabilizes. Okay, it's not, it has stabilized. I cannot say it's a constant. Yeah, see, it's little bit varying also, right? So I cannot say it's a constant, but it stabilizes. See, it's the same. The concept is the same. That minimum amount of, I am going to pick up the minimum amount of cost, right, with which will give me the maximum benefit. Okay, so this is there is going to remain some 0.05 dispersion, whatever margin I take after that. Okay, so 0.05 becomes my third one. Third is the 0.05. Okay, it becomes my optimal margin. Okay, quickly, how many of you have done the confusion matrix, got the accuracy? How many of you have done confusion matrix type C? Type C, if you have done the confusion matrix quickly. Okay, thanks Bharat. Thanks for confirming. Right. See now, Bharat, you should start understanding, start interpreting the errors. Right. See, Very clearly it is saying SVM is not found, means library is not run. It does not find SVM means, right, the library, you have not run the library command. Okay. Okay, quickly, others, have you calculated the accuracy? Confusion matrix, type C in the chat window if you have done. Okay, fine, fine. Not an issue, Bharat. Continue. Type C in the chat window if you are done till 97. Accuracy, 98% accuracy. Maybe you might be having slightly more or less, but that's the accuracy that is coming. 0.96. Okay, fine. See, there is a difference because, the numbers are, so the data points in test and train, they might not be exactly divisible. So because of that, little bit, yeah, variation can be there. Yeah, random selection can also differ, right? Okay, done. Can I proceed? Can I proceed to the next model? Naive Bayes. We'll do a theory of Naive Bayes and tomorrow we will run the model. Okay. Naive Bayes. Can I start with Naive Bayes? I'm not getting response. Kindly respond. Kindly respond. Okay, sure, Bharat. I'll take, no problem. I'll take a minute. I'll take a minute to start then. Thanks, Tarun. Thanks, Aarti. Appreciate your response. Okay, can I start now? Right? Okay, great. So, we have come a long way. I know it's overwhelming, but yes, we have to continue the momentum, and I'm sure you are learning a lot of things here, right? And this is only a start. Don't take it as a conclusive that you have done entire machine learning or entire data science. No, you have just scraped the surface. Take it like this. Okay. Okay, with R as well as the as well as the concepts of machine learning also, right? Okay, classifier. We know what is a classifier. I just discussed. A classifier is a machine learning model that is used to discriminate different objects based on certain features, right? Classification is coming from classifier only, right? What is naive based classifier? A naive based classifier is a probabilistic machine learning model that is used for classification tasks. The classifier is based on Bayes theorem, right? We'll discuss Bayes theorem, hence the name naive Bayes. Okay. The Bayes theorem is used to calculate the conditional probability, which is nothing but the probability of an event occurring based on the information about the events in the past. Notice, Bayes theorem is used to calculate the conditional probability based on the historical data, okay, that you have, which is nothing but the probabilities calculated based on the historical data. It makes a strong assumption. Now, that is why it is called naive. That the strong assumption is that the the predictors or the features are independent, and we have seen in regression they many a times they are correlated, right? But when you are sure that your predictor variables are independent, because this is the assumption with naive Bayes, that is the presence of one particular feature does not affect the other, means the independent variable, right? One independent variable does not impact the other independent variable. This is the strong assumption which it makes and which in real life does not apply, right? That is why it's called naive, because of that. To make it a simplistic case, we make this assumption, right? So if you are sure you are analyzing some data and you are sure that the independent variables are completely independent, are actually independent, and they are not correlated, then naive Bayes is a very good classifier model you can use. Okay, so let's understand the uh, this Bayes theorem, right? Bayes theorem calculate the probability of A. Now this A slash B means A, probability of A assuming B has occurred, right? So this A slash B, now you don't have to, of course, you don't have to remember the formulas, but I'm just explaining what is the Bayes theorem. Okay, probability of A assuming B has occurred. So that is a posterior probability, right? And means the probability that we are trying to calculate. Probability of class A happening given the predictor B has already occurred. Okay. Similarly, PB slash A, likelihood of predictor B given the class A has already occurred. And probability of A is PA, probability of B is PB, right? Now, this I'll explain. PB minus this plus this, I don't know. Yeah, you can leave this red part. It's just the same thing. I have just moved it on the other side of equal to. Okay, now let's understand naive Bayes with the help of this example. A very interesting example. This is my training data, right? This is my, on the extreme left is my training data. Based on the training data, below, we need to classify if the players will play based on the weather condition, right? Or the play will happen. Whether weather conditions are there, so weather conditions is your X variable. And the play will happen or not is your variable you want to predict. Okay, so historically when you look at the data, whenever the weather was sunny, in first instance play did not happen. Then you have data of overcast weather, play did happen. On a rainy day, play did happen. On two, now this data on 2 sunny days previous, right, rain play happened. Similarly, overcast, rainy, sunny, right? So I have collected data for 14 days, right? 14 days historically, and this is how was the happening or the occurrence of play. Sometimes play happened, sometimes play did not happen. So I create a frequency table from it, right? I create a frequency table and plot the occurrence and non-occurrence of play. Okay, and after that I calculate the likelihood. Pretty simple logically, if you think, it is one of the most simplest of the algorithms to understand, because all of you know probability and this is all based on probability, right? Overcast, when it was overcast day, play happened 4 times, and there was no overcast day when play did not happen. Notice, right? And what is the probability of this play happening on an overcast day? Oh, sorry, this play happening, it's 4 by 14. But now tell me, if I give you that, now this 4 by 14 is clear, 4 upon 14 total, right? Now tell me, if I give you that that I pick up that on a next day, after my tomorrow is a overcast day. Tomorrow weather forecast is overcast. So what do you think is the probability of play occurring? Play having, I mean, the play will happen. If tomorrow is a overcast day, there is a weather forecasting that tomorrow is going to be overcast. What do you think is the probability of the play happening? Did you get my question? Did you get my question? I am saying Yes, Vijendra. Excellent. Understand, Vaibhav. I am saying tomorrow is a overcast day. So what is the probability of the play happening based on historical data on every four overcast day play happened? Okay, this is the probability based on the total data. But I have given you now a condition. That is what Bayes theorem says. Given a probability of A given B. I am now giving you, so it is a conditional probability. I am giving you a condition that tomorrow is going to be a overcast day. So probability will be 4 on 4, right? 100%. Everyone got it? Right? So that is what Bayes theorem is. So similarly, if I say tomorrow is going to be a sunny day, so what is the probability that the play will happen? Tomorrow is a sunny day. What is the probability that a play will happen? Hmm? Is it 66% or 60%? Forget what is written here. Why? 3 upon 5. Oh, I'm saying tomorrow is a 33 into 2. No, 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 don't see this. Don't see this. This is some different example. I'm coming to that. I'm saying tomorrow is a sunny day. So what is the condition I have given? It's sunny. So what is the probability? Why 1 by 3? Where is 1 by 3? Yes, right, Sachin. Yes, Vaibhav. Getting it? Uh, 2 by 3? No, it's 3 upon 5. Vaibhav, why are you getting confused? Vaibhav, 3 out of 5 times play happened on a sunny day. Now tomorrow is a, yeah, full say, no, no, you don't have to divide by the full, you'll only have to divide by the sunny observations. Yeah, yeah, 5, yes, yes, right. Okay, got it? So that's what we do in naive Bayes, right? That is how you calculate the probabilities in a naive Bayes, right? Okay, so now another, you can, it is not this way, you can also try to predict the weather also. If tomorrow you are sure, if on a particular day play happened, what is the probability that it was sunny? Play happened means this. What is the probability it was sunny? 3 upon 9, right? Other way, right? 3 upon 9. Got it? Okay, so that's all we're going to do today. And tomorrow, when we start, we'll continue with the naive Bayes and then we'll move over to uh, more classifiers, decision tree, and random forest. Okay, hopefully you have learned, you have enjoyed, and keep practicing, and that is going to really help you a lot. Okay, keep practicing. You'll come across lot of more complicated situations, more complicated data sets. Start working on them. So it's your journey has just started. Okay, it's not ending on a day after tomorrow, right? Okay, thank you so much. Take care. No, Angela, we don't. I don't think I will have time to touch on the projects. But yes, I will give you the coordinates. Give you my coordinates. If you have any doubt, you can just reach out to me. Okay. Okay. If you, I'm saying, I'll share my coordinates. Right. If you have any doubts, you can definitely reach out to me. Okay. Okay. Then take care. Goodbye and see you tomorrow. Thank you.